Hello, welcome to the Nimiq podcast. This is Richie, your usual host. Today we're going to be talking about zero knowledge proof, and to talk more about it, we have here two experts that have been working into integrating it into the Nimiq blockchain, Pascal, Berrang, and Inês, Cruz. Guys, how are you feeling?
Yeah, good.
Right.
Quite warm today, but good.
Yeah, it's a little bit warm here. We're in Costa Rica in the Silicon Paradise area, and it's quite warm. So thanks for taking some time and joining us and telling us more about zero knowledge proof. The first question I have for you is actually, what are zero knowledge proof? Can you explain me like I'm five?
Sure, we can do that. I can start with a very simple example, like let's say you just bought some ice cream of your favorite flavor, and your friend comes over and asks whether you have ice cream, and now you want to prove to your friend that you have ice cream without revealing which flavor of ice cream it is, in which container it is, and so on. And you could do that with zero knowledge proof, basically telling a friend, look, I have ice cream. I will not tell you anything about the exact specifics about the ice cream, but I can prove to you, and you will be convinced afterwards that I do have ice cream.
So a more concrete example would be, I guess you've played Where's Waldo when you were a kid, right? So you have this massive thing, and Waldo is somewhere there, you don't know where, and you have to find it. So there, what you can do is just put this opaque paper on it. You put a hole just to show that will be sufficing and showing Waldo there. And then you put it there and you show this person, look, here is the drawing of the Waldo. You cannot really see where exactly in the frame, in the whole problem it is, but you know it exists and it is there.
And you basically prove that you found Waldo.
Yes.
Yeah,
Proved.
that's the most important part, without revealing its exact location.
So without taking the fun away from the other person. Right?
Yeah, exactly. You can tell the other person, look, I know where Waldo is, you still don't, and I can prove to you that I know where it is.
Yeah, so now figure out there.
Exactly.
Very interesting. So it's like a cryptographic way of proving that you know some information without disclosing all the information.
Correct. Exactly. That's the zero knowledge part of it. The word consists of two parts, zero knowledge and proof. The one part, the proof part, is you want to convince the other person that you know the answer to a certain statement, and zero knowledge means that you do not want to reveal everything about your solution.
Okay, and this is I've been hearing it a lot, but recently, like in the last 2 years maybe. And I know that with everything that has been going on blockchain, then cryptography had a boost in research and amount of people getting involved. How recent is this technology, zero knowledge proof?
I mean, it is an old kind of tech. However, it hasn't been really used since 2012. Like, it was applied at least for cryptographic reasons.
Exactly. So I think the first papers around the topic probably started to appear around the 1980s. So actually quite old. But these were mainly feasibility or impossibility results. There was no actual system around, maybe for very specific use cases. But the first real zero knowledge proof systems that could prove more than just a very specific statement, they started to appear around 2012, as you say. I think the CK snarks, as we know them today, and since then quite a lot of development has happened in the area.
And you just mentioned these CK snarks. I've heard CK snarks, I've heard CK starks. Are there other like Starks or other things? Are there more types? What are the types for zero knowledge proofs?
Yeah, there are quite a bit. So you mentioned CK snarks and CK starks. These are two different types of the underlying system, how they work. CK snarks work with elliptic curve cryptography, and the CK starks, they are more based on hashes. And so they all have different properties, and other systems have been introduced since there are bulletproofs, and also within CK snarks there are differences, and every different proof system comes with a different trade-off. So you could have one that needs a trusted setup, which means that you need to to generate something in the beginning before you can start proving and verifying stuff. And during this generation, there also comes something usually that is called toxic waste, and you need to destroy that, otherwise you can fake proofs, and you don't want that. Others don't have that, and maybe some have a constant proof size, others have a variable size proof, and different things.
Definitely. You can also have like interactive and non-interactive ones.
Correct.
What's the difference between those two?
So interactive makes it so that for me to prove something to you, I will be multiple, like we are going back and forward in communication. So a good example is like you cannot really so I have these two pens, and like I don't know if they are different or not, so they look the same to me. I can scramble them, and then you can tell me straight away, look, that you scrambled it, or no, they are in the same position, imagining that I'm colorblind, for example. So I don't believe that you see different colors, and you can show that because you can obviously see that there's two different colors. So if you do that once, I will not be very convinced, because you could just be lucky. It's 50% chances. You said, yeah, you didn't change it, so the black and the red are here. So you can have 50% chances. But if I do this enough and you always get it right, I know that you know something that I cannot really understand.
Okay, so this is a version maybe that has some memory.
Basically, I think the interactive zero knowledge proofs, they work based on probabilities. So maybe if you show me one statement that you do to convince me about the statement you want to prove, you show me something, the probability of you getting this right is, as you say, it could be 50%. Then I'm not really convinced. It could be just your luck that you got it right. But if you do that a second time and you're right again, well, the chance of being right 2 times is 25%. If you do it another time, the chance of you being right by chance and not actually knowing the solution decreases and decreases. And you can do that a couple of times until the other person is convinced, well, that's not just luck, it's actually that the person knows what they're talking about, or they have the solution to the statement.
That's more clear. Thanks a lot for the explanation.
And I guess we can also briefly introduce the card example that we were talking about before.
The card.
With the cards.
But it's not interactive. Is that the one you talked about?
I mean, it's not interactive, that's true.
The interactive ones.
Yeah, but we can. I mean, now we talked about the about the interactive ones, and we could use that as.
Let's give an example of the non-interactive.
Do we have a card game here?
We don't, and I thought about the pens just to show, because it's hard to explain. But
yeah.
All right. So in a regular deck, you have 50-50 black and red. So imagine we scramble this. He takes a card. I don't know the card. I didn't see it. There is no magic trick here.
Mm-hmm.
So now you would prove. You would tell me
a red one.
You have a red one. Okay, but like he might be acting in bad faith. So how do I know that it's actually red? So. But
I do not want to disclose to her what the number is, or so what specific card it is. I only want to prove her that I have a red card and nothing else. So what could I do? I mean, I could show her the card, but then she knows what card it is. I could show her all the other red cards in the deck, but then she can, because she knows what the deck consists of, she can deduce which card I have. So what's the solution?
So the solution would be just to show all the black cards there. There's all of them. I know that you cannot have a black one, and I see that you have a card. So now I know, yeah, your card for sure is red. I don't know which one, and that's exactly what we wanted.
That's a nice example of zero knowledge proof.
Okay. Yeah, that's very, very clear. Now that we understand better what are zero knowledge proofs and some examples and what types we have, now let's talk about the specific implementation for Nimiq. Is there something very specific about our implementation of zero knowledge proof?
Specific in the sense that we were some of the first to actually use that. Yes, we do use zero knowledge proofs that are recursive. And not all zero knowledge proofs actually support this recursion. And I mean, what does it mean for recursive proof or for zero knowledge proof to recursive? it means that in the proof we can prove another proof, and in that proof we can prove another proof. So it's doing a lot of things in this very small constant size thing. And that's one of the things that is maybe a bit more specific about our approach. It uses some elliptic curves. We're using CK snarks, and we're having two different curves that we use, and they fit together very well in a way that you can actually, on one of these curves, prove statements about the other one, and the other way around. And that makes it so that we can use the recursion to take a proof that, for example, we know the blockchain from A to B, and we can extend this proof and say, okay, we also know it from B to C, and we get a new proof from A to C. Yeah,
Transposing. Yeah.
exactly.
Anything to add?
Maybe we can say that in terms of verification time, it's decently efficient. That's what also allows for our web client to work, and then we are already explaining why we are actually using them. So recently we actually managed to speed up the whole thing 100 times. So maybe you can go on it.
Yeah, sure. So yeah, currently the verification in the web client of the whole blockchain takes 600 milliseconds. Previously it was taking 60 seconds, which was, to be fair, not a problem of the zero knowledge proof. It was more a problem of the very first implementation we had. It was recomputing things quite often, although we wouldn't need to do that. And it took us a bit to find out where the problem was, but in the end we managed to. And
so basically by avoiding recalculating the same thing multiple times, that is quite an expensive calculation, we managed to speed up the whole process by 100 times, which is quite cool.
And can you tell me a bit about that calculation? I've heard some things of like the size of the number, the sheer size of this number, the calculation, how many zeros does it have? That is why it takes also, so long.
Yeah, so I mentioned before that we use elliptic curves, and the numbers we're using, they have a specific size. They are quite big. So if we normally talk about numbers on a computer, they are how many bits would you say? 32, 64? Depends on your system. 64 bits, let's say.
64.
Yeah. And that's the biggest number the computer can hold in one of their smallest units, and that's what it can efficiently deal with and efficiently calculate things with. Now, the numbers we use in the zero knowledge proofs, there are 753 bits compared to 64 bits. You see, the numbers are now huge, very big. We still need to calculate stuff with them, but the computer can only deal 64-bit numbers, and that means it takes a bit.
Because also each bit it grows like exponentially, the size of this number, right? That's the idea. I mean, from 32 bits to 64 bits, there is a big difference, right? And each bit that we add to the size of this number is actually grows exponentially, because some people could say like, 64, that doesn't sound a lot, but go 2 to the power 64. That is like, I don't want to even start saying that number. And then go to 2 to the power of that. I mean,
adding one bit, the number you can represent doubles. Yes,
exactly. And it grows exponentially by adding each bit, grows and grows and grows.
Correct.
Yeah.
That's very, very interesting. And it sounds like, is there anything else specific that you want to talk about our implementation?
I don't think so.
I heard also we were discussing about the amount of time that it takes for computations to take. Like, so basically it is a proof that, how does it work? It's like there is some code, and then we generate a proof of that code so that clients can basically verify the blocks of the blockchain. And then when we generate this proof, it takes a lot of time, at least the first time, or the nodes take a lot of time, like generating the proof. How often does it happen? The generation of the proof?
Okay, so basically we are generating one of these proofs for every epoch. That means that we are waiting for an election block. So when the first election block comes in after the genesis, we are going to start generating a proof. But the generation of the proof takes around 6 hours, depending on the machine you have. Like, depends on the capabilities it has, and then you have and you have to wait that time so that you have the proof and you can finally use it, because it takes its time to be generated from the prover node side. That's only generated by the prover node, by the way. And then it's finally can be used by other clients, and the other clients just pick it up and, okay, let's verify that it is accurate and proving that the chain does go until there. And from then on, they can continue syncing if that's what they are doing, and they don't have to go through every single block one by one. They can skip a whole bunch of them to the proof that succinctly shows that from Genesis until that block, this blockchain exists and is valid.
Yes, exactly. And as you said, the proving takes quite a long time, around 6 hours on a capable machine, but the verification takes only 600 milliseconds. And that's why we use them, because, well, our epochs are designed to be around the length of the proving time, but then the verifier, the web client, can use this very succinct small proof, and it gets the whole blockchain basically proven that there is a valid transition from A to B in this very short statement, and we can verify it very fast.
Okay, that's very cool. And now, some last question, because I'm curious about this. It sounds like there is, like, with this long computation time, like, it's kind of interesting to work with that. What is the funniest, most challenging thing about working with zero knowledge proof in the testnet?
Yeah, I guess the most challenging thing is actually the waiting time. If you change something in the code and you want to know, does it work? Can we generate a valid proof? Well, we do the code change, we push it to the server, we start it, and then we wait 6 hours, and maybe in between we see it didn't work, or we wait 6 hours and then we see it worked. It takes a very long time. It's very different from other development. Yeah.
Yes, definitely. And then it can be teasing all this time until almost the 6 hours, and then finally fail. That's the cherry on top of the cake. Yeah.
So all this development and research that you guys have been doing for Nimiq Proof of Stake, I think now when we release this video, the testnet wallet is going to be out already. So when, like, now with all this technical explanation, when a user goes to the testnet wallet, when is the zero knowledge proof magic happening?
Right in the beginning. The first thing that happens is you download the zero knowledge proof and you skip that part of the blockchain, so that the client, the wallet has a client built in, so that one is then convinced that the current state of the blockchain is there.
So that's pretty much the first thing to do, because the first thing is to get on to the most recent information that the blockchain has stored. And the way to do that is, let's get the most recent zero knowledge proof we have, and from then on we can finally sync the rest way more easily, because the blockchain grows over time, right? There's blocks and epochs all the time, and after a while it would take forever and be impossible to use in a web client. With the zero knowledge proof, then we get it in instants.
And maybe there's one more question actually to you that I remembered. Now we talked a bit about zero knowledge and zero knowledge proofs. The zero knowledge part obviously means you don't want to disclose something. Why do we need a zero knowledge part? What is the thing we want not to disclose in our zero knowledge proofs?
That's a good question.
What do you think?
So I would think the history of my transactions, which could be linked to my identity in some way.
Well, it's not a very bad answer. I think you're getting to the point,
maybe,
but not the right reason.
Maybe the history of the transactions, because that takes a lot of time.
Correct. So the part that we do not want to disclose is actually public. It's the blockchain in between. But by saying zero knowledge, we don't want to disclose it. I mean, if you want, you can, because it's public. But in the proof, we don't want to disclose it, just so that you don't have to download it. You don't have to download the whole blockchain. We give you a proof that shows you that there is a valid history from the beginning to the current state.
Amazing. Thanks a lot. Thank
Yeah.
you for joining me, guys. Remember then to subscribe, add any comments for Pascal and for Inês to answer if you have some questions, and see you in the next one. Bye.